So to talk about quantum entanglements, I want to first talk about a concept of correlation. I think that's really the starting point. So let's imagine a scenario with you and me, and we have very basic, boring wardrobes. Let's say that I only wear orange and blue shirts, and you only wear orange and blue shirts. Now, you could imagine that one is keeping track of the shirts we wear each day, has a chart. Monday I wear orange, Tuesday I wear orange, Wednesday I wear blue, etc. And you could do this for many days. You would accumulate a long list of colors, right? You'd look at this list and it would be somewhat boring. You do the same thing for your shirts. Write down the colors that you wear each day. So we have two lists of very boring information, just colored shirts. Okay, but now suppose that we take those lists and we put them together. We might find something interesting. We might find, in fact, that we have matching color choices. Okay, so what have we done here? We've taken two relatively boring lists, put them together, and something interesting has emerged. What's emerged is what we call correlation. It's the fact that we have matching choices of our shirts on each day. Okay, so this is very interesting. And you could ask, well, how would we form this correlation? Right? Why do we have these matching statistics? Well, one way you could form it would be, imagine in the past you and I got together and we had some calendar, let's say, right? And we wrote down each day of the week what color shirt we'd wear. So we had this plan ahead of time. And then we photocopied the calendar. You had one copy, I had another copy. Bang, we go our separate ways. And now each day we just check our calendar and we wear the shirt. All right, great. So we have a mechanism for how we can generate this correlation. All right. In fact, it turns out that all types of correlation that we experience in the classical world, or the world described by Newtonian physics, can be described in this way. There's some sort of shared instructions. In our case, it was the calendar. But there's some sort of instructions that have been distributed to the different systems that's explaining how they should behave. Okay, that's kind of the classical picture of how correlations emerge. Now we turn to quantum systems. These are systems, very small scale, systems that are under precise control. We can do the same thing. We can imagine that there are two or more systems that are separated from one another. And just like our t-shirts have properties, color, size, style, quantum particles also have properties. So we can measure those quantum particles like we measured our t-shirts. Create lists, right? So we make our measurements and we have our lists. And again, individually these lists look pretty random and boring. And you'd say there's nothing interesting here. But now when you bring them together, you can find that they're correlated. Now here's the key point. When you look at these quantum correlations that emerge, it turns out that sometimes you can't explain them in the same way we were able to explain our t-shirts. We explained the t-shirts, recall, in terms of the shared calendar, the shared instructions that was distributed to both you and me. For quantum systems, you can't always do that. So that begs the question then, what is the mechanism that allows for this type of correlation between the two systems? And that mechanism is what we call quantum entanglement. So what is quantum entanglement? Well, it's a property of two or more quantum systems that allows them to be correlated in ways that we can't describe using classical descriptions, or descriptions that are familiar in Newtonian mechanics.